this equivalent mechanical system, okay, is on the basis of nodal method. Okay, it is on the basis of nodal method in the sense each displacement is represented in the form of a node. Okay, that means to say theta is considered as a node. Okay, this is for rotational system. And X is also considered as a node for a translational system. Okay, so in the rotational system, we are going to consider theta as a node. And in case of a translational system, X we are going to consider as a node. Okay, and some spring constant K and some frictional constant B is given. And the mass of the system is also mentioned. And it is given that the linear force is applied in the following direction. That means to say the force is getting applied from left hand side to right hand side. Okay, so in this direction the force is getting applied. Okay, so in the direction of force there will be a displacement. Okay, so let us consider the displacement as x of t. Okay, this is your given mechanical system, which is comprising of the three fundamental elements, right? Of frictional coefficient B, the spring constant K, and the mass of the system M. Okay, now whenever you have been given with a mechanical system of this kind, first thing what you have to do is you need to understand or you need to mark the displacements. Okay, how many displacements you're going to have. Okay, just to recall, okay, quickly, I think in class number 6 or class number 5 we discussed about it, right? You know that element M or element J will always have one displacement. Okay, I'm just saying the displacement. I'm not talking about angular or linear displacement. That's because right, for a rotational system it is angular displacement, and for a translational system it is linear displacement. Okay, so element M or J will always have one displacement. On the other hand, element K and element B can have two displacement, or it can also have one displacement. Okay, when you can have two displacement? When both the terminals of K and B are allowed to move freely. If both the terminals of K and B are allowed to move freely, then you can have two displacements. On the other hand, if one of the terminal of K and B is rigidly connected to a reference frame, then it can have only one displacement. Okay, so though in this particular problem the displacement is already been given to you, okay, still you should inspect this particular system. Okay, whether the given displacement is right or wrong, it is up to you to decide. Okay, that's because in your exams, okay, as well as in competitive exams, sometimes they themselves will give the displacement. Okay, sometimes they will not give the displacement. They may give or they may not give. If they give the displacement, well and good. If they don't mention the displacement, then it is pretty tricky. So you are supposed to identify the displacement in that case. Okay, assume that the displacement is not at all given in this particular mechanical system. So you have to inspect the system, and you have to predict how many displacements this particular mechanical system is going to have. Okay, now observe carefully. The entire system is under the influence of one forcing function, that is f of t. Okay, now whenever f of t is applied, okay, you know that mass element undergoes linear acceleration, spring element undergoes linear displacement, and the damper or undergoes linear displacement. Now mass, as I mentioned, it will always have one displacement. So just mention that particular displacement. So let us say that displacement is x of t. Okay, so mass will always have one displacement. Done. We have identified the displacement at mass. Okay, now let us look at the damper and the spring. Okay, spring and damper can have two displacements, provided both the ends are moved to freely, right? But over here, you can see that the terminal 1 of spring K is connected to mass, and mass is already under the displacement x of t. Okay. On the other hand, terminal 2 is rigidly connected to a reference frame. Hence, there cannot be any secondary displacement at the spring element. Okay. Similarly, if you look at the dashpot, you can see that terminal 1 of dashpot is directly connected to mass m, and mass m is already under the displacement x of t. Okay. On the other hand, the terminal 2 of dashpot is connected to a rigid frame, hence it cannot have the secondary displacement. Okay. So the three elements are under the displacement of x of t. So for this particular system, there's only one linear displacement, which we have considered as x of t. Okay, so once you identify the displacement, so let me write step 1, identify the displacements. Okay, you can go to step 2. Okay, now in step 2, what we will do is we will represent each of the displacement as a node. Okay, so basically we are going to represent each of the displacement as a node. Okay, fine. Now in step 3, what we do is connect the elements which are under the influence of one displacement in shunt manner. Okay, or instead, okay, let me just write it in a straightforward manner. Okay, connect the elements which are under the influence of one displacement. Okay, between the respective displacement and the reference frame. Okay, connect the elements which are under the influence of one displacement between the respective displacement and the reference frame. Okay, I will explain you the meaning of step 3. And step 4 is the final step, is about placing the elements which are under the influence of two displacements. Okay. Place the elements which are under the influence of two displacements. Where are you going to place? In between the nodes. Okay, place the elements which are under the influence of two displacement in between the nodes. In between the nodes. So, place the elements which are under the influence of two displacement in between the nodes. On the other hand, the elements which are under the influence of one displacement needs to be connected between respective displacement and reference frame. Okay, so fine. Let us try to construct the equivalent mechanical network. Okay. Fine. So how many displacements did we identify in the given network? Only one displacement. So mark that displacement and name the displacement. Okay, so this is your node. So wherever I'm mentioning that connect the elements between the node or between the nodes, okay, what we mean is the displacement. So node is nothing but a displacement. Okay. Now identify the elements which are under the influence of two displacements. Do we have any elements which are under the influence of two displacements in this given problem? Are there any elements which are under the influence of two displacements? No, right? Because we have identified only one displacement in the given problem. Okay, so step number 4 is not applicable for this particular problem because there are no elements which are under the influence of two displacements. So all elements are under the influence of one displacement alone. Okay, so what you have to do is on one side you mark the displacement and on the other side you mark the reference frame. So this is your reference frame. All right, and the elements which are under the influence of one displacement, you're going to place them between the respective displacement and the reference frame. So this is my respective displacement. Okay, in between the reference frame and the displacement, I'm going to place the elements. So this is my mass element. Okay, you look carefully. The mass element has been placed between the respective displacement x of t and the reference frame. Similarly, the dash part is also under the influence of one displacement, hence the respective reference frame, sorry, the respective displacement and the reference frame. So this is B. And similarly, you have your spring element K that is also getting connected between the respective displacement x of t and the reference frame. Okay, finally you write down the forcing function in a similar manner between x of t and the reference frame. So this is how you construct the equivalent mechanical network on the nodal basis. Now, this nodal basis network mechanical system, okay, is quite similar to the KCL network. This you will understand when we talk about something known as analogous systems. Don't worry about it. I'll tell you maybe in the future classes. Okay. Okay. So, is it clear how to construct the equivalent mechanical network?
Yes, sir.
Okay. Great. Fine. So once the mechanical network, okay, is constructed, you can go ahead to write down the differential equations. Okay. So what we will do is one node. So opposed to write the differential equation. Okay. Consider the fact that
Sir, we can't hear you.
the applied force F of t, okay, the applied force F of
Sir, we can't hear you
velocity.
again.
Okay. And also this particular force equation is called as D'Alembert's principle. Let me put it in check box. This is called as D'Alembert's principle. F of t is equal to Fm of t plus Fd of t plus Fk of t. Okay. Which is quite similar to your Kirchhoff's voltage law. That is, supplied voltage is equal to voltage across, let's say, resistive element, inductive element, and capacitive element. Okay, so which talks about law of conservation of energy. Okay, in the similar way, the D'Alembert's principle is also being stated. Okay, so f of Fm of t in bits and pieces, you had written the differential equation, right, for a mass element. Over what you have to do is you have to collate the results. Okay, for a mass element, it is m into d square x divided by dt square plus for a dashpot, it is b into the velocity function, which is dx by dt. And for a spring element, it is k times the displacement. Okay. You can also write, double differential function as x double dot, a single differential function as x dot. Okay, and x of t, you need to write it as x of t itself, right? So equation 1 is your time domain equation, and you convert it to Laplace domain. F of t becomes f of s. The double differential function becomes s square into the displacement, okay, multiplied with displacement, plus b into single differential function, which is s into x of s, plus k into x of s. Okay, so this is your Laplace transform. So this is what I was explaining when I had lost you guys. Okay, so is this clear?
Yes, sir.
Okay, fine. So we investigated a simple linear system, right? So now let us try to investigate a rotational system. So for that case, what I have considered is a 3-element rotational system consisting of moment of inertia J, spring constant K, and coefficient B. Okay, and the objective is already set. Construct, firstly, what you have to do, you have to construct a mechanical system on the basis of nodal. Okay, and you're supposed to write the differential equations as well. Okay, so fine. The torque is getting applied in the clockwise direction, right? So this is the direction of torque. Okay, now you guys have to tell me this particular system is under the influence of how many angular displacements. So this is a rotational system, right? So you need to talk about the angular displacement over here. So can anyone tell me how many displacements this particular system is going to have? Okay. 1, Nirmala is saying, quickly, don't worry about right and wrong. Quickly, can you type few answers? The inertia element will always have one displacement. Okay, no questions asked because it cannot undergo deformation. So only one displacement. That is in the direction of applied force. On the other hand, K and element B can have two displacements provided you are allowing both the terminals to move freely or not. Now, in the given problem, you can clearly observe that terminal 2 of element K and terminal 2 of element B is rigidly fixed, so it cannot have any displacement at terminal 2 side, right? So it can have only one displacement. Okay, so terminal 1, it is directly connected to inertia element J, and terminal 1 of dash pot is also connected to inertia element J, and inertia element will be under the influence of, say, displacement theta of t. Okay, so this particular system will have only one displacement, which is theta of t, which is in the direction of applied torque t of t, so in the clockwise direction. Okay, all right, so once you know the displacement, what you can do is you can represent that particular displacement as a node. So this is our node. Okay, and what is the node value? Theta of t. Okay, and then you also mark the reference frame in this manner. Okay, and then you start collecting the elements which are under the influence of one displacement as well as which are under the influence of two displacement. Now, step number 4 is invalid in this particular case due to the fact that there are no elements which are under the influence of two displacements. So element J, it is getting connected between node theta of t and the reference frame. So this is my element J. And similarly, element B, it is getting connected, okay, across the respective displacement and the reference frame. Okay. Similarly, element K, it is getting connected across the respective displacement theta of t and the reference frame. Okay. Finally, you have your twisting force function, which is nothing but torque t of t. Okay. So this is your equivalent mechanical network. So objective 1 is met, right? Now let us try to answer question number 2, that is write down the differential equation in time domain as well as in Laplace domain. So what you do is apply the torque equation at node theta of t. Okay. So let us try to write down the twisting force equations at node theta of t. Okay, so what I will do, motoring torque, okay, not motoring torque, you can say that external torque which is applied at theta of t is equal to torque consumed by element J, okay, torque consumed by element B, and the torque consumed by element K. Okay, so in bits and pieces I have written. So T of t is equal to, okay, Tj of t. What is Tj of t? It is basically, the torque absorbed by element J. So that's nothing but J into theta double dot plus Tb of t, which is nothing but torque absorbed by the dashpot, which is B times the angular velocity. Angular velocity is single differential function, and the torque absorbed by element k to cause the displacement, right? Angular displacement. So that is k times theta of t. So this is your time domain representation. Let's write down its Laplace domain equation. So theta of t is t of s, and j into, it's a double differential function, so s square into theta of s plus b into single differential function, which is s into theta of s, plus k into theta of s. So this is your differential equation expressed in Laplace domain. Okay. So this is how we are supposed to solve these problems. Okay. Now, to start off, I have considered a very simple problem. Okay. Now, let's start considering complex ones also. Okay. Now, did you understand the idea? Did you understand? Even if you can understand the logic, it is well and good, because as you start solving, 2 or 3 problems, you will be able to understand better and better. Okay. Did you understand the logic? If yes, take problem number 3. If no, also you take problem number 3. Okay, let me consider a kind of complex system, and then let us try to see how exactly we are trying to construct the equivalent network. Okay, all right. So write down in the given system shown below. In the given system shown below, obtain the transfer function. Obtain the transfer function. Okay, and this is the given system. Okay, it's a rotational system. Some moment of inertia J. Some K1 and some B1. So this is the reference frame, and this represents B2, and this is K2. Okay. Okay, all right. And they have given the direction of torque, T of t. Okay. So this is the given system, and you are supposed to find the transfer function. Okay. Okay. Now observe this network carefully. Okay, and try to identify the displacements. Don't worry, this transfer function later we can write, because I have to tell you what are the signals, right? Because in order to find the transfer function, you need to have your input signal as well as you need to have your output signal. Input signal, pretty straightforward. It is the torque, T of t. Okay, and the output signal, I'll tell you a little later once you identify the displacement. Okay, can anyone tell me how many displacements this particular system is going to have? Take your time. You take about 2 minutes of time. Okay, great. 2. So this particular system will have 2 displacements. So let us mark the displacement. So First displacement directly here you can mark, let's say theta 1 of t. Okay, that's because in the direction of torque, there will be an angular displacement. Okay, now element J will always have one displacement, no questions asked. Now element K and element B can have two displacement, provided you're allowing both the terminals to move freely or not. Okay, now let me first mark the terminals. Terminal 1, terminal 1, terminal 2, terminal 2. Okay, now terminal 1 of K1 and terminal 1 of B1 is directly connected to J, and J is already under the influence of theta 1 of t. Done. Now let us pay our attention to terminal 2. Now terminal 2 of K1 and terminal 2 of B1, is it rigidly connected? Is it connected to reference frame? No, it is not connected to reference frame. Instead, it is connected to K2 element as well as B2 element. Okay. Since the terminal 2 of K1 as well as B1 is not connected to reference frame, so there can be a secondary displacement theta 2 of t. Okay, so there can be a secondary displacement theta 2 of t. Okay, all right. Now let us move on to the remaining elements. Okay, element B2. Let us mark the terminals, terminal 1 and terminal 2. You can flip, doesn't matter. Now terminal 1 of B2, where is it connected? It is basically connected to the junction of K1 and B1, okay, which is already under the influence of theta 2 of t. On the other hand, terminal 2 of B2 is connected to a reference frame, hence there cannot be a displacement. Okay, so you cannot have a displacement at terminal 2 of B2. Similarly, you can also analyze element K2. Now, terminal 1 of K2, where is it connected? It is connected to the common point, right? The common point where B2 and K1 and B1 meets. And this particular point is already under the influence of theta 2 of t. So, terminal 1 of K2 is already under the influence of theta 2 of t. Okay, fine. What happens to terminal 2 of K2? Will there be any displacement? No, there cannot be any displacement. That's because terminal 2 of K2 is rigidly connected to a reference frame. So this particular system will have two displacements. Okay, so each displacement needs to be marked as a node. So this is your node 1, theta 1 of t, and this is your node 2, theta 2 of t. Okay, and then you mark the reference frame. Okay, reference frame. Now, what you have to do is you have to identify the elements which are under the influence of one displacement. Okay, look at element J1. Okay, so this is J1. All right. Now, J1 is under the influence of displacement theta 1 alone, right? So you are supposed to place J1 across its respective displacement. And what is its respective displacement? Theta 1 and the reference frame. Okay, so J1 is having only one displacement. So we have placed J1 across its respective displacement theta 1 and the reference frame. Okay, done? Okay, now let us go on to displacement theta 2. Okay, and let us identify the elements which are under the influence of theta 2 alone. What are those elements? Element K2 and element B2, right? Because you can clearly observe that terminal 1 of B2 is under the influence of theta 2. Similarly, terminal 1 of K2 is under the influence of theta 2. Okay, what about its other terminals? Terminal 2 of B2 and terminal 2 of K2. They are rigidly connected to the reference frame, hence it cannot have the secondary displacement. So B2 and K2 is connected between theta 2 and the reference frame. So this is your B2 and this is your K2. Okay, so we are done with the elements which are under the influence of only one displacement. Okay, J1 is under the influence of theta 1 and B2 and K2 they are under the influence of theta 2 alone. Okay, now let us identify the mutual elements, in the sense the elements which are under the influence of theta 1 as well as which are under the influence of theta 2. Which are those two elements? K1 and B1. Right. So K1 and B1, they are under the influence of theta 1 as well as theta 2. So just connect them as the mutual element. So let's say this is your K1 and let's say this is your B1. Right. That's it. And then you identify the torque. Okay, so torque is getting applied at theta 1 side, right? So this is your torque, T of T. Okay, and this is your equivalent mechanical system, okay, which is being drawn on the basis of nodal analysis. Okay, and the end task is to obtain the transfer function theta 2 of S divided by T of S. So this should be the transfer function. Okay, let me solve in the next class. All right. You can even try. Okay, no, since you know, you can make an attempt. I'll keep it as homework. Keep this as homework. Okay, so try to identify or try to find out the transfer function theta 2 by T of S. So I'll give you the hint also. So what you have to do is you have to write down the differential equations. Okay, write down differential equation at displacement theta 1 of T as well as at displacement theta 2 of T. So remember one thing, this is one rule of thumb. Number of displacements is equal to number of differential equation. Okay, so this is the rule of thumb. Number of displacements is equal to number of differential equations. Okay, so please try out